All right, so this is going to be one of a few videos that I'm recording on the overall topic of chemistry of conjugated dienes. We're going to look at UV-vis spectroscopy. We're going to look at kinetic versus thermodynamic addition across conjugated dienes. And then we will look at pericyclic reactions, of which there are three types: Diels-Alder, electrocyclic reactions, and sigmatropic rearrangement. So probably do a video on each one here to break it up. So first things first. Okay, so let's start off by reminding ourselves what exactly we're talking about when we say conjugated dienes, right? Because all of these reactions and these topics are all with respect to conjugated dienes. So you remember from your Orgo 1, if you have something like that, that is an alkene. If I have two double bonds, that's a diene, three double bonds, that's a triene, etc. So conjugated dienes means I have this type of an arrangement where I have alternating double, then single, then double bonds. And to remind you, this is what we mean by conjugated diene. And of course, you can have conjugated polyenes, right? So you can have, for example, not only two, but I could have a whole series of double bonds conjugated. And you see the arrangement double, single, double, single, double, single, double, single, double. That's what we mean by conjugated. If I had, for example, a situation like this, just for comparison, if I had double bonds here and here, those are isolated double bonds. On the other hand, if I had that 5-carbon chain, those double bonds are now conjugated. And just to complete things, there's also a class of molecules we draw like that. These are what you call your cumulines, or cumulated, isolated, conjugated, and cumulated double bonds. So we're interested in the chemistry of the conjugated dienes. Now, one of the things we already know from previous classes is that a conjugated system is going to be more stable than the isolated equivalent or the isolated system. So let's remind ourselves of why that happens to be the case. So we can always do these reactions in order to test this out. So here's typically what we'll do, how we can prove that conjugated dienes are more stable than isolated. If we take 5-carbon ring, 1 double bond, if we go ahead and we do a hydrogenation, right? So we're going to treat this with hydrogen. What we'll end up getting is pentane. So what we can calculate here is what is the heat of reaction, what's the enthalpy of reaction for this particular process, and it ends up being minus 126 kilojoules per mole. So if I now take, let's say, this, which is the isolated version, what you expect, because now we're doing the hydrogenation to two double bonds, so we have to use two equivalents of hydrogen, then what you would expect in this case would be that the delta H would probably end up being 2 times what you got for one of them, 126. So you would expect about 252 kilojoules per mole. You would get the exact same product. What you actually get, so what do you actually get in a case like this? So the actual delta H ends up being minus 253 kilojoules per mole. So right about where you expect it to be. Now, if I take the conjugated system, which is that, again, if we do a hydrogenation with two hydrogen molecules, I'll get the same thing. Again, what you expect would be 2 times minus 126 because you have 2 double bonds. The actual delta H that you end up getting for this is minus 236 kilojoules per mole. So if you end up getting less energy when you do this hydrogenation of the 2 conjugated double bonds, that means that this must have been lower in energy than that. You end up at the same energy point, the pentane. So if you give off less with a conjugated, it must have been lower in order to give off less. Well, if I compare the isolated version here versus the conjugated version here, the difference between 252 and 236 is about, sorry, 253 is what you get here versus 236. The difference is about 17 kilojoules per mole of energy. So that means that's how much more this one, the conjugated, is more stable compared to the isolated by about 17 kilojoules per mole. So there's the evidence that indeed conjugated systems are actually more stable than isolated systems. So then we ask ourselves, why, right? What would be the reason why conjugated systems would be more stable than isolated? And there are two arguments that are put forth. So the first one is an argument based on bond strength, and the second is an argument based on molecular orbital theory. So let's look at the first one. Let's look at the argument when it comes to the bond strength idea. So if I have the isolated versus if I have the conjugated, what we do here is an analysis of what types of orbitals are involved in overlap for each bond that you form. So for example, and I'll put numbers here so that you follow the discussion more readily. If I look at bond between carbon 1 and 2, so let's say C1 to C2, what I have is an sp2 to sp2 overlap. When I look at carbon 2 to carbon 3, what I have is carbon 2 is sp2, carbon 3, however, is sp3. If I look at the carbon 3 to carbon 4 overlap, carbon 3 is sp3, carbon 4 is sp2. So just to keep it consistent, I'll say sp2 to sp3. Again, clarifying that the sp2 is for the C4 and the sp3 is for the C3, but just to keep it consistent. And then the C4 to C5 overlap, both carbons 4 and 5 are sp2 hybridized, so therefore sp2, sp2. So if I do carbon 1 to carbon 2 here, both carbons are sp2 hybridized, so the overlap is an sp2, sp2. The carbon 2 to carbon 3 overlap, both carbons 2 and 3 are sp2 hybridized, so that would be sp2, sp2. The carbon 3 to carbon 4 overlap, both of those carbons are sp2 hybridized, so that'll be an sp2, sp2 overlap. And finally, carbon 4 to carbon 5 overlap. Carbon 4 is sp2 hybridized, carbon 5 is sp3. So where do we see a difference? Let's eliminate those that are the same. So this is an sp2, sp2 that is matched by that. I have here an sp2, sp3. I have one here. I have another sp2, sp2 here that is matched here. And then you see where the difference lies. Here, we have an sp2, sp3 remaining versus an sp2, sp2. If we want to narrow this down more specifically, we can say both of them have an sp2. So therefore, the actual difference is in an sp3 here versus an sp2. So an sp2 orbital, remember, has 33.33% s character, whereas an sp3 bond has only 25% s character. right? 1s and 3p's for a total of 4. The 1s out of 4 is 25%. If it's an sp2, 1s and 2p's, 1s out of the 3 is a third. Remember, s orbitals are closer to the nucleus, so electrons in them are held more tightly, making that bond more stable. So since I can identify a bond with a conjugated system here that has more s character, you can see why that would be more stable, and that would be a reason why. The alternative, or the second way we can actually go ahead and describe this, is MO theory. So with MO theory, we're looking at bond overlap. So if I have an isolated system here, what it means is that these are isolated so that I have, in each case, an sp2 carbon and an sp2 carbon. So let's say if I focus on this one, it has 2 carbons that are coming with sp orbitals. There is an electron in each one. And if those orbitals overlap, there are 2 ways that this can happen. Their amplitudes are going to match. So we show that by shading both sides, or the amplitudes are not going to match. So you see there's no match there. And by now you know this system, we mean there is a node there. So these would be your molecular orbitals that you'd get from the atomic orbital overlap. And you have 2 electrons, so 2 of them go there. So here's your bonding molecular orbital, and that would be your antibonding molecular orbital. But the thing is, that is what would happen with each double bond individually and in an isolated fashion. So those electrons, right? What that means then is that the electrons that we have here and the electrons that we have here, in each case, those are localized electrons. They cannot move anywhere else. They're localized between those 2 carbons. On the other hand, if we now have a conjugated system like this one, then the difference is I have 4 carbons. So we have 4 carbons, each one coming with the unhybridized p orbital, where you're going to try for overlap to see if you'll get constructive interference or destructive interference. And again, to remind you, there is an electron in each of these atomic orbitals. So if these waves try to combine, there are 4 ways in which this can happen. So the most stable arrangement is going to be this one, where what happens is amplitudes in the 4 waves match, and we show that by showing all matching shaded and unshaded. Then there's 0 nodes there, and node, remember, is a site of instability. And then a second way in which these waves can combine is that these 2 match, the amplitudes match, and these 2 match, but you see right here, you have a mismatch, so that would be a node. So that's a different orbital. The third way in which this can happen is that you get this one not matching this one, but these 2 match, and that one doesn't match. So wherever there's a mismatch, you have a node, so you notice you have 2 nodes. Every time you have more nodes, that's less stability. And then the worst case scenario is that these 4 orbitals, none of the amplitudes match. So this doesn't match this, which doesn't match this, which doesn't match this, which means that we have 1, 2, 3 nodes. So we go from having 0 nodes in the lowest one node, the next higher one, 2 nodes here, and 3 nodes there. So we're going in increasing energy. And the higher energy you get, the less stable this is. So I have 4 electrons, so I have to place them 1, 2, 3, and 4. And the reason why this conjugated system is very stable is that we get this particular arrangement that allows the 4 electrons now not to be localized, but to be delocalized. Because what's happening here is that if I have carbon 1 here, and it is forming the pi bond with carbon 2, and then we have carbon 3 here, which is forming its bond side-to-side overlap pi bond with 4. But because those 4 carbons are sp2 hybridized, those orbitals are perfectly parallel, which means that the electrons are freely shared throughout the four carbon or four atom center rather than being localized. And that would explain why that is the case. Now, since I've shown you here the molecular orbital diagrams, let me remind you that when we're doing these, again, remember energy is increasing in that direction. These would therefore be your bonding molecular orbitals. They are lower in energy than your original. Here's the level of your original atomic orbitals. And these would be your antibonding molecular orbitals that have no electrons. So two very important molecular orbitals that we always want to identify when we're working these MO systems is what is the highest molecular orbital that is occupied by at least one electron. And I think you can see that that would be this one. So that we classify as the highest occupied molecular orbital, the HOMO orbital. And then we also want to identify what is the lowest molecular orbital that has no electrons. So as I go down, right, I have electrons here at the HOMO. So the lowest molecular orbital that is totally unoccupied is this one. So this is the lowest unoccupied molecular orbital, which is the LUMO. So HOMO and LUMO orbitals are very important. And here is where the HOMO and the LUMO become very important. So now let us look at the whole idea of UV-vis spectroscopy. All right, just so that I don't have to redraw everything here, I'm just going to erase these and start the whole discussion of UV-vis spectroscopy. So UV-vis spectroscopy. So here is the theory behind this. Where do we use UV-vis spectroscopy? So we use UV-vis spectroscopy to measure the extent of conjugation that an organic molecule might actually have. So this is what we mean by this. This is how the system actually works. So you see our four orbitals that we have here, right? So four molecular orbitals, two bonding, two antibonding. Now, there is an energy difference, an energy gap, of course, between the HOMO and the LUMO. So between here and here, there is an energy gap. There's a difference in energy. So this is what we call the HOMO-LUMO gap. How much energy do we have? It turns out that the gap, the size of that gap, gets smaller with increasing conjugation, meaning the following. If I have, let's say, two double bonds conjugated versus if I have three double bonds conjugated versus if I have four double bonds conjugation. So as I'm going in that direction, I'm getting increasing conjugation. So what happens as the molecules have more conjugation is that the energy difference between the HOMO and the LUMO gets smaller. So the delta E, this gap here, is getting smaller. So as we go from 2 to 3 to 4 double bonds conjugated, that means the HOMO-LUMO gap, in other words, that difference in energy, gets increasingly smaller. And the reason why that is important is that we already know what's the equation to find the energy. The energy is, of course, one of the equations is it is Planck's constant times the speed of light in a vacuum over the wavelength. So I'll remind you, there's an inverse relationship between energy and wavelength. As the energy gets bigger, the wavelength gets smaller. As the energy gets smaller, the wavelength gets bigger, the wavelength associated with that energy. So if we are saying that as you get increasing conjugation, the HOMO-LUMO gap, the difference in energy, the magnitude of that difference in energy gets increasingly smaller, then you realize we're also saying that as you get increasing conjugation, because the HOMO-LUMO gap gets smaller, that means then the wavelength associated with that energy gets bigger. And this is how we can tell or test for how much conjugation, the extent of conjugation that we have in a given molecule, because we can measure that wavelength, right? The wavelength associated with that magnitude of energy, which is the difference between the HOMO and the LUMO gap. This wavelength, the lambda, is what we call lambda max in our instrument. And that lambda max is what a UV vis spectrophotometer is actually going to test. And that's really the extent of what we use UV vis spectroscopy for the most part in organic chemistry. So let me show you here what we mean by the wavelength or the lambda max. So here is an example. So here is the molecule 1,3-butadiene. And this is what a UV vis spectrum is going to look like. So on the x-axis here, we have the wavelength. On the y-axis here, we have the absorption. And you notice this is why we don't use UV vis as we do mass spec, NMR, and IR, which give us much more detailed spectra where we can put structures together and find functional groups. Here, this is how a typical UV vis spectrum looks, right? You're going to see essentially one, maybe two, maybe three peaks. So where this curve maxes out, which is here, we come down here and we find where it crosses the x-axis. What that wavelength is what we call your lambda max. That corresponds to the wavelength associated with the energy of the HOMO-LUMO gap. Now this absorbance, you see this little a here. We notice that there's a formula to calculate it. It is the log of I0 over I. I0 is the incident radiation, I is the exiting radiation, meaning the following. If I have a UV lamp here, I'm going to direct the UV radiation like that. If I put here a cuvette with my sample in the path in between the UV vis lamp as a source of the UV radiation and my detector that I have here, then what happens, of course, is that before this incident, this UV radiation hits the sample, we can say its intensity is I sub 0. Some of that intensity will decrease as that UV radiation traverses through the sample, so the exiting intensity is actually less. And if we take the log of the incident radiation intensity over the exiting radiation intensity, that gives us the absorbance, right? So that's really what we use UV vis for. So here's an example. Notice how the lambda max is changing when I go from 2 double bonds conjugated to 3 double bonds conjugated to 4 double bonds conjugated. So the lambda max is 217 when it's 2. It goes up to 258 when it's 3 double bonds conjugated, and it goes up to 290 when it is 4 double bonds conjugated. And you see if we had 5, 6, 7, 8, 9, 10, that lambda max keeps getting progressively bigger and bigger and bigger. Now, if you will recall, the range that we call visible region ranges from about 400 nanometers to about 800 nanometers. Now, most people really only see up to 700 and something, but there is a small subset of humans who genetically can see up to 800. So we say that's the range of visible. So you see we're going from 217, 258, 290. You realize that if there are enough double bonds conjugated, you can actually get that lambda max to fall above 400, which then fits into the visible region. So we call this technique UV vis spectroscopy, not just UV spectroscopy, right? So what else should I say here? Let me see if it's somewhere here. I want to show you, well, here, let me just do it. So we calculate the absorbance using this equation. So let me go back to where I was. All right, you go here and say the following. We always need to standardize things, right? So comparing absorbances or absorption is not very good because different people might be running their instruments under different conditions. So what happens is we agree to run all UV-Vis experiments under the same conditions. And instead, what we calculate is a standardized parameter. It is what you call the molar absorptivity. And the molar absorptivity, which has this symbol, is equal to the observed or calculated or measured absorbance from your UV-Vis spectrophotometer over the concentration over the path length. So this here, of course, is what's going to be experimentally observed in our UV-Vis spectrophotometer. The C is the concentration of the solution of our sample. We all agree on a set one molar concentration. And the L is what we refer to as the path length. So remember I said you put your sample in a little cuvette, right? So your sample is going to look something like this in the path between the UV-Vis lamp and my detector here. So when we measure the distance between here and here, that distance, the distance that the UV-Vis, the UV radiation has to traverse in that little cuvette is what we call L, and that is standardized, so the factories sell the same length. So the only thing that we measure here is the absorbance. Concentration is standard, path length is standard, plug the equation in there and we get a standardized value, which is the molar absorptivity. And now we can calculate, we can compare molar absorptivities to see if we have the things that we do. So a quick thing now, by now you know I don't really like to get into this kind of discussion where students feel like they have to memorize values and numbers and so on, because for the most part, when you're working in the real world in a lab, right, when I'm doing my research, I have access to tables and things like that. I don't memorize these things, but I want to show you this to go over the concept. So here, we are talking about the absorbance. And we see how as you get more conjugation, the lambda max increases. So a question that we might have is, can we actually predict for given situations, can we predict what the lambda max is going to be if the molecule gets a little bit more complex? We can, and this is using what you call the Woodward and Fieser rules, right? As a note here, these rules were developed to predict what the lambda max happens to be for a chromophore. So if you've been, if you know anything about chromophores, these are things that are very colorful. And when you have organic substances that have a high degree of conjugation, they tend to be chromophores and be very colorful. So for example, tomatoes have lycopene in them. Lycopene the molecule has a lot of double bonds conjugated, and therefore it's a chromophore and it's very colorful, which is why tomatoes are very colorful. Same situation for carotene, beta carotene, which you find in carrots. So those particular things tend to be very colorful. So here's how you apply the Woodward and Fieser rules, right? Notice in a situation like this. So we were talking about, notice strictly 2 double bonds, 3 double bonds, 4 double bonds. There's nothing else hanging off that. However, here we have highlighted the chromophoric part, which would be your 4 double bonds. Anything that is extra is what you call an oxochrome. So in this case, you have here an ethyl group that's an oxochrome, and you have a methyl group. Those are not the chromophoric part. So if we know that 4 double bonds, as we saw here, when we have 4 double bonds, the lambda max is 290, but there is nothing else except the 4 double bonds here. What happens when I attach an ethyl group there and a methyl group there, which is what I did here? How does the presence of those things, the ethyl and the methyl group, which are your oxochromes, well, and in this case, sorry, I didn't see here, another methyl and another methyl, how do they affect the lambda max? So here are the rules. If we have, for example, just a regular 2 double bonds, we saw that the lambda max is 217. So that's our base value, 217. For each additional double bond that we have, because remember, this whole chapter is in conjugated dienes. So this is the only diene. If I start adding double bonds, then I go to trienes, tetraenes, pentienes, hexaenes, and so on, polyenes. So for each double bond that I add to my base diene, I add 30 to the lambda max. So since I have added 2 additional double bonds, I will then say 2 times 30 here is 60, add that to the 217, and I would predict that it should come out somewhere around 277. And notice that the observed value is 290, close enough within experimental error. Now, if I have oxochromic groups, if the oxochromic groups are alkyls, such as here I have methyl, methyl, and methyl, for each oxochromic group that you have that is an alkyl group, you add 5. So again, in this case, I have only 2 double bonds. That's your regular base here, 217. I have 3 alkyl oxochromes. 3 times 5 is 15. Add 15 to the 217, and I would predict that the lambda max would be 232. Notice that it actually is 232. So this one hits it exactly in the nail. If I have here, right, the diene being what is called an exocyclic alkene or an exocyclic double bond. In other words, notice one double bond is within the ring, the other double bond is outside the ring, so we call that an exocyclic double bond. So if I have here a diene, so that's just a regular base 217. If it is for each exocyclic double bond that we have, we actually add 5 to it, right? So we're adding 5 for the exocyclic double bond. And for, go back here, each oxochromic alkyl group is adding 5. So in this case, if we focus only on the conjugated, which is this part that I'm circling, then we consider this an alkyl oxochrome, and we consider this an alkyl oxochrome. Each one is 5, so 2 times 5 here is 10. So 217 plus the 5 for the exocyclic double bond, plus 2 times 5, 10 for the 2 alkyl oxochromes, we would predict 232. It's actually 230. And then finally, if we have what's called the homular dienes, that's where you notice both of the double bonds are within the ring here. Then you add 239 to the base 217, so that would be 217 plus 239 for the homular diene. And then if I encompass here the diene, then this represents an alkyl oxochrome. This represents an alkyl oxochrome. So does this one, and so does that one. Each one is 5, so 4 times 5 here would be 20. 20 plus 39 added to the 217 gives us 276. That's what we would predict. We get 269. So you see how the Woodward-Feser rules allow us to predict with a high degree of accuracy. They're not necessarily like precise, but good enough, close enough to what the observed values are that we can do those predictions. And really, this is it for UV-Vis spectroscopy. We're just looking at the extent of conjugation. So the typical kind of question that you're going to see here is going to be something like this. Look at the following molecules and say which one will have the largest lambda max. Well, This one has 0 conjugation. This one has 2 double bonds conjugated. This one has 3. More conjugation, the smaller the lambda max. So that would be your answer for the smallest lambda max, right? Something along those lines is what we typically get.